So now we have the next talk by, what is the right name to pronounce?
Jurij Volčič.
Jurij Volčič. Okay, it's Jurij Volčič, and he's from Drexel University, and the title of his talk is Invariant noncommutative rational functions.
Okay, thank you very much. Thanks, Artem, for inviting me. I mean, I've been enjoying this workshop a lot, and I mean, the topics resonate with me. So this is joint work with Igor Kleb, James Pesco, and Gregor Podlogar. So James is my colleague here in Philadelphia nowadays, and Igor and Gregor are from Ljubljana. I'll talk about non-commutative rational functions that are invariant for certain groups. But I'm actually going to first start with saying what non-commutative rational functions are, because it's not too many people know what they are. Okay, so to set some notation and so on. So this little k is going to be a field for most of the talk. At some point, it's going to become algebraically closed of characteristic 0. This underlined x are going to be freely non-commuting variables. And then here we have then free algebra, whose elements I like to call non-commutative polynomials, right? So because they look like polynomials, just the variables don't commute. And now for non-commutative rational functions, right, you would kind of like something along the lines of, well, for commutative polynomials, you just take a field of fractions, right? And these are rational functions. And now I would like to do something like that for free algebra, right? I would like to take field of fractions. Now, of course, these are not real fractions because things don't commute, but we probably kind of have some idea how non-commutative rational functions should look like. That said, one needs to be a little bit careful. And the reason why one needs to be careful is that, well, whenever you have non-commutative rings, how they embed into skew fields, meaning in division rings, that can be a bit tricky, right? So that there's this old result of Maltsev saying that, well, not every non-commutative ring without 0 divisors embed into a skew field. And the other thing is, even if you can embed your ring into a skew field, there might be many non-isomorphic smallest skew fields that you can embed your ring into. And in particular, that happens even for free algebra, right? So Fisher constructed a continuum of non-isomorphic fields of fractions of the free algebra, right? So, okay, there's many fields of fractions of free algebra. Is one better than the others, right? And this is what we're going to call non-commutative rational functions. And we can, I'm going to describe one construction, and this is, that's how it was done originally by Amitsur, right? I mean, like many other nice things in non-commutative algebra, it all goes back to Amitsur. So what do you do? First, you take your, you take the variables x1 to xn and scalars, and you start forming all formal rational expressions, right? So things that involve addition, multiplication, and inverses, right? And it needs to be just syntactically valid, so the parentheses should make sense, right? So you get this kind of expressions. Now, if I just do that, I probably, you know, when I'm doing this, I can do something stupid stuff, right? If you look at this last expression, and you really think, okay, if I really plug in some evaluation, some concrete x1, x2 from some division ring, then this last thing should not make any sense, right? It looks like an inverse of a 0, right? So just building this syntactically valid formal expressions, it's not gonna give you, not all gonna make some sense. So then you do what Amitsur did. So you fix an infinite dimensional skew field that contains the base field, so not the other way around. Sorry about the typo. And then for each expression, you can talk about the set of n tuples from this skew field such that R of x is well defined. What do I mean by that? Well, there are some inverses in here, so you only want to take those tuples where all the inverses are going to make sense for a given expression. And then among all expressions, first you throw out those that are never well-defined. So for example, this third expression here is never well-defined. And then on the rest, on the other expressions, you define a relation. You say, well, two expressions are equivalent if their evaluations agree on the intersection of their domains. And then one can prove that this relation is actually an equivalence relation. So once you do equivalence classes, you can define additional multiplication of them. You get a ring. You actually get a skew field. And the most important thing, it's independent. This construction is independent of the choice of D. Right. So if you don't like infinite dimensional skew fields, you can also do the following. Instead of an infinite dimensional skew field, you just take the set of all tuples of square matrices of any size over the base field, and then you repeat the same thing. You say, given an expression, you take the domain of the expression or the tuples of matrices that evaluate on this expression that makes sense for this expression, and then you say, okay, two expressions are equivalent if they agree wherever they are both defined. So so the equivalence classes, so the skew field that I got, that's independent of if I start with matrices or with an infinite dimensional ring. So this is then called the free skew field of non-commutative rational functions, and we use this funny notation for it. So I think Paul Moritz-Kohn was the one that introduced this notation. So this skew field is, in a sense, it's a universal, so in some precise sense that Kohn defined. I like this definition because I like to think of rational functions as really as functions. Of course, if you don't like this evaluation procedure, construction, you can also say, there's many different constructions of this skew field, right? You could also start with a free group generated by x1 to xn. Now, this free group, you can put a total order on it that's compatible with the group structure, and then you do Maltsev-Neumann series over the free group. So that's a huge skew field, and within it, if you take just the skew field generated by the generators, that's gonna be precisely this free skew field. So it's an interesting. So it's not an unnatural object. One of the things why it's somehow hard to work with it is that you see, rational expressions are given by, functions are given by expressions up to this equivalence relation, and sometimes it's, it might not be completely obvious when two expressions give you the same function, right? So actually, these two, if you really look carefully and think about it, these first two expressions, they actually define the same rational function. So wherever for x1s and x2s, for matrices, they are both well defined, they give you back the same. Okay. Now, who cares about non-commutative rational functions? So, they started with work of Amitsur and then Kohn and so on. They became really prominent in ring theory through quasi-determinants that were. So this was a big body of work done by Gelf and Deritak and so on. But I think independently of that, they also, maybe even earlier, arise from theoretical computer science, if you want, automata theory. So Schützenberger, probably the main figure, and then Reutenauer. And in control theory as transfer functions of linear systems in control. And then a bit more recently, they appeared in computational complexity, right? So this is from the question is, if I give you a rational expression, how do I determine if it represents the zero rational function? So it's a rational identity testing problem. So this has it shows up in computational complexity. And then finally, as I said, we like to think of these NC rational functions really as functions in matrices, and then this leads to non-commutative real algebraic geometry and non-commutative analysis. Okay, but what I want to talk about today are invariants, right? So from this moment onward, I'm gonna fix K algebraically closed of characteristic zero field. And now if I have let's say a finite group acting linearly on n-dimensional space. We typically then, this induces an action on the polynomial ring and on the rational functions, but it also induces an action on free algebra and on non-commutative rational functions, right? So then the NC polynomials fixed by G are called NC polynomial invariants, and NC rational functions fixed by G are NC rational invariants. And now, of course, the basic problem is, well, can we describe the structure of these rings? Right? So in particular, I'm going to focus on a rational invariant. To get us going, I want to focus on probably the simplest possible example that's already interesting. So let's say that I think of polynomials and rational functions in only two variables, x and y, and I have S2 acting on it by just switching the coordinates, so switching x and y. Then an old result from Wolf says that the bivariate NC polynomials invariant under dissection, they form a free algebra generated by freely generated by this infinite set. So here I have an infinite family of invariant polynomials. They don't satisfy any common polynomial relation, and then and all other invariant polynomials that are generated by this infinite family. Okay. So this is pretty old. And now something that was pointed out quite recently, essentially, was by Agler and Young, that, okay, I mean, these generators are actually, so here I have infinitely many generators, but if I only take the first three ones, so this x plus y, and then this x minus y squared, and x minus y, x plus y, x minus y, if I take these three are enough if you want to generate all the other generators with rational operations, right? Because you can write down this kind of formulas, right? All the further generators, they express like this, right? So here I have inverse appearance. Okay, now we look at this, and then you can go a little bit further. You can show that actually all invariant rational functions are generated by these three polynomials, and these three polynomials are really independent in the sense that they don't satisfy any rational relation among them. So the invariants are generated by these three polynomials. So this is kind of the first interesting example, right? I mean, you immediately see that, okay, polynomial invariants are free algebra on infinitely many generators. Rational invariants are free skew field in three variables. Okay. Now, in general, for polynomials, and I think we're going to have some more talks tomorrow in this direction. So in the morning, Drinsky and Bomo are going to talk more about symmetric non-commutative polynomials and so on. So in general, polynomial invariants are essentially never finitely generated, at least our field of characteristic zero. We'll hear tomorrow what happens with finite characteristic, if it's any different. So whenever you have a finite group, then the polynomial invariants are a free algebra on infinite set, generated by an infinite set. So not finitely generated, unless in a very special case when the group action is really just scaling by a primitive root of unity. And in that case, you get finitely many free generators. So of course, more can be said, certain other things, one-sided co-invariants, Hilbert series, so on, standard, non-commutative versions of standard symmetric bases and so on. But at least if I'm kind of being ignorant and I really just focus on the pure ring structure, it's kind of they all look the same, right? Free algebra on infinity many generators. And this is a little bit different once you look at rational invariance. So one of the results that I'll talk about is that if you have a finite solvable group acting linearly on free skew field, then the invariants are always finitely generated as a skew field. Before I say more about this result, there's already a few open questions here. So first of all, is solvability of G really needed? We don't know. We simply, you'll see by the methods that I use it somehow why we only know stuff about solvable groups. And actually, the second thing we also don't know is, well, okay, say here finitely generated. Is it a free skew field? Are these generators, can you always take them to be rationally independent? We'll see that for certain groups, or rather for certain type of actions of G, we can conclude that, but in general, we don't know. And actually, this leads me to kind of a Lurov type problem that's also open. Is every skew subfield of a free skew field again free? So this is unknown. This is unknown. We were actually hoping that maybe we're going to find some example by looking at this invariants, but it's unclear what's the answer. Okay, now the base case. So okay, instead of proving this theorem, I want to talk about more precise theorem whenever my group is abelian. So if you have a finite abelian group acting on n-dimensional space, then the rational invariance, NC rational invariance, is a free skew field on this number of generators, right? So order of G times n minus 1 plus 1. So when you see this number, you kind of you can already suspect a little bit how the proof is going to go on. Maybe before I go on, I should say that you know, for non-commutative, so for free skew fields, of course, you can embed free skew field on infinitely many variables into, let's say, free skew field on two variables. Nevertheless, whenever you talk about minimal generating sets of a free skew field, the number of generators is really a property of the free skew field, right? So I mean, it's not like you can freely generate it with different numbers of generators, right? Yeah. So okay, how does this proof go on? So okay, it's a finite abelian group. So first you diagonalize it. So then on the monoid, on every non-commutative word, G just acts like multiplication by some scalar, so by character. So that actually gives you then, okay, now if I embed free monoid in the free group, then that gives me surjective homomorphism from the free group into the character group. Okay, now the kernel Niels-Schreier theorem, right? So subgroups of free group are free itself, right? And even more, we know how many generators you need for it. So Nielsen-Schreier theorem tells me that. And then this kernel, if you generate a subfield in the free skew field with it, it's again going to be free, right? So that's a result by Lewin, right? So this is kind of interesting because, you know, if I just take a few non-commutative polynomials that generate a free algebra, it doesn't mean that they are going to automatically generate a free skew field. Or at least it can happen that polynomials don't have a polynomial common relation, but they do have a common rational relation. On the other hand, if I really start with some elements from the free group, if they are free as elements of the free group, they are also generated free skew field. And finally, in this case, when you have a finite abelian group, you can show that actually rational invariants are generated by polynomial invariants. So then that was the reason why it suffices to look at what's happening with the invariant subgroup of the free group. Okay. Now, so this was for abelian groups. I was saying something about solvable. So what do you do now? So how do we leverage this result to say something about non-abelian groups? And the idea is the following, right? Okay, so if I have a non-abelian group, okay, you take a normal abelian subgroup, then let's call it N, then N invariants are free on finitely many generators by previous theorem, and then the quotient group G over N acts on these N invariants, right? And now, if you're lucky, if this new action of this quotient group, if this is still linear, then you reduce the problem to the quotient group. So this might be a big if, right? So, but this is the idea. If you can do that, then you can, start going further, right? So, and whenever you can do that, this is not just about groups, right? This really depends on what kind of representation you have, what kind of action you have. So group representation that allows this reduction, let's call it nice. I'm skipping the definition because it's kind of a technical, but there's a definition, a rigorous definition attached to it. Instead of giving you this definition, let me give you a related definition. So it's really a definition on the group, a recursive definition, a little bit like how you would define a solvable group, right? You say that, okay, if I have a finite group, if I take a non-trivial normal abelian subgroup of G, then I say that G is unramified over N if whenever you take any irreducible representation of G, then the restriction to N is either trivial or splits into distinct irreducible representations of N. And then you recursively say, okay, group is totally unramified if it's either abelian or it has a non-trivial normal abelian subgroup N such that G is unramified over N, and then the quotient is totally unramified. Okay, so this definition is not, it's not, it doesn't look completely unnatural, right? So the reason why I'm mentioning it, because you can show that if you have a group like that, then the left regular representation of such a group is nice. Now, from definition, it's kind of clear that every totally unramified group, it's in particular solvable. Now, what are some concrete examples of totally unramified groups? Well, abelians, of course, and then furthermore, metacyclic dihedral and more generally semi-direct products of abelian ones, also S4. And actually, when you go in GAP and you run calculations in GAP you can find all the irreducible representations and so on. You find that the smallest example of a group that's not like this is of size 24. Is this SO2 over 3 element field? Okay. So the theorem, as far as you can push it, is that if you have a group with a nice representation, then the invariants are going to be free on that many generators. So in particular, a totally unramified group acting on G-dimensional space, left regular representation, then it's free on that many generators. I do want to now show an example of kind of what's stopping us to not be why we can't really go further, and maybe it's going to be an instructive example. So consider the following. Again, I'm just going to have two variables, x and y, and I act on with the dihedral group d4. I act on it. So the dihedral group, right? You have a rotation and reflection, right? So on x and on y, it multiplies them by I and minus I, right? So I is square root of -1, and b, the element b is the one that swaps on x and y. Now the dihedral group, every dihedral group is totally unramified, but you see total unramifiedness tells you something about the left regular action. This concrete representation is not nice. Again, I didn't give the definition, but it's not nice, and we'll see now in what do I mean by not nice. So you say, okay, I'll try. I have normal abelian subgroup, so this Z4 sitting inside. So I can first compute the invariants for Z4, and these are free on these 5 generators, right? So by the theorem that I had before on abelian groups. You can actually also find the generators, and then the quotient, so Z2, acts linearly on the 4 of these generators, right? It switches, right? At Z2 it's going to switch x and y, so it switches Z1 and Z2, it switches Z3 and Z4, but then on Z5, so it sends it to y to the 4, right? But y to the 4, it's not a linear combination of these generators, right? So that's kind of the problem, that the quotient doesn't necessarily act linearly on your generators. that said, it's not the end of the world, right? I mean, you can replace this last generator Z5, you can replace it by this Z5 prime. And this was kind of a, I don't have a good reason why we did that, right? It was an ad hoc, you try things out, right? So you define Z5 prime like this, right? So then, yeah, you can replace Z5 by Z5 prime. And Z5 prime, it's x squared plus y squared times the inverse of y squared minus x squared. So the point is, this Z2, it sends Z5 prime to minus Z5 prime, right? So now that I kind of by hand replaced one of the generators, now Z2 acts linearly on this, and then, well, that tells me that the whole thing is free on 9 generators. So somehow we don't, I mean, somehow why I can't say more about other solvable groups, it's more like we don't know what to say. It's not that we have an actual honest-to-God structure. And now to wrap up, let me just say a few words about maybe the most interesting case, right? If you have a symmetric group acting on variables just by permutations. Okay, n equals 2, we already saw. N equals 3, it's also free on 13 generators because this representation of S3 on 3-dimensional space is a nice representation. And it's also true for S4. So Podlogar, one of the co-authors, later proved that the S4 acting on 4-dimensional space by permuting coordinates, it's also a nice representation. Right? Okay, so for these 3 cases, we know that the symmetric n-rational functions form a free skew field. Of course, we don't know what happens for n equals 5 or higher. Right? So we're going to need some new method to talk about that. Okay, so again, just to summarize, right? So free skew field, how universal skew field of fractions of the free algebra, while polynomial invariants are almost never finitely generated, rational invariants are finitely generated, at least for solvable groups, and actually free for certain nice group actions. Right? But as you see, we have more questions than answers. So is the subfield of a free skew field again free? Like the Murat problem, we don't know. We also don't know what happens with symmetric n-rational functions when n is 5 or bigger. Okay, thank you.
Okay, thanks a lot for your talk. Are there any questions or comments?
Yeah, may I?
Okay. Yes.
Is it known the automorphism group in the case of 2 variables, like in the commutative case is generated by Shear-Narson transformation?
Yes, no, that's not known. That's not. So what is known is in 2 variables, polynomial automorphisms are known, and they are somehow they are actually the same as in the commutative case. So affine change of coordinates and the triangular ones, or how do you call them? But the rational automorphisms are not known. The rational automorphisms are not known even in two variables.
So it's also not known which are finite groups of automorphisms.
Yeah. So for example, we don't know. I mean, we don't. It's not known if you would have some kind of a small generating set. You don't have description like Cremona group, right? As you said, fractional linear transformation. We don't know if those are enough.
Okay. So lots of things.
No, lots of things. Yeah, I mean, as I said, there's less things known here than less known than known. Maybe one thing that I should mention. Well, one thing that I find interesting. Again, we can be on 2 variables, right? So if I think of all like if I act by GL2, general linear group, on this, right? There's not going to be any polynomial invariance because GL is just too big. If I would do SL, it would not be too big, but GL is too big. On the other hand, there are non-trivial GL2 invariant rational functions in 2 variables. And again, we don't know, you can construct a few, but you don't know are they finitely generated or stuff like that.
Okay, thank you.
Okay, thank you, Claudio, for your questions. And Yuri for your answer. Are any other questions or comments? No, I can't see. Okay, so then let's thank the speaker again.
Thank you. Thank you.